Hey everyone, so let's talk about Riemann sums and integrals. So again, I'm going to use GeoGebra Classic. It's just what I prefer to use. And let's go ahead. We'll use a trig function again that's maybe a little bit above the x-axis. So I will go 2 sine of maybe 0.5x to spread it out a little bit. And I'm going to raise that up 1 so we have a little bit below the x-axis as well. And I want to create a flexible endpoints for my Riemann sum. So I'm going to place a point over yonder here. And I'll place a point over here. Now there's a couple of different flavors of these Riemann sums, and all of them will require some sort of a slider to control the number of subdivisions that we have. So I'm going to name my slider n. And so I'll go n equals slider, and I want my slider to go from 1 subdivision to maybe 50 subdivisions by steps of 1. And then I will, let's make our first one. So the first one would be a lower sum. So the commands typically work the same way. This is a lower sum. I'm going to give it the function name, the starting value, ending value, and the number of rectangles, because this will build rectangles, but the height of all the rectangles is determined by the lowest function value on any interval. So I will call this lower sum f, and then the x-coordinate of point A and the y-coordinate of the x-coordinate of point B, and I want there to be n subdivisions. And then as I drag my slider around, and this is super flexible, I can drag that left and right. And again, if I just look at it like that, the area is negative because the area is all below the x-axis. So this is a nice tool. Likewise, let me go ahead and hide this. There is an upper sum, which is defined the same way. And these rectangles, the heights of the rectangles are all based on the greatest function value on that interval. So you could see as I increase the number of subdivisions, these two values get closer and closer, they sandwich the true value in between. So that in and of itself is a really cool visual for what is happening with the integral. Let me hide those. There's another one that is called the trapezoidal sum. Trapezoidal sum works the same way. I'm going to take the function, my x-coordinate of A, the x-coordinate of B, and I want to have n subdivisions. And this is also, I think this is cool. When you go to 1 subdivision, it is a trapezoid. But of course, this value, the area of those trapezoids, will always be between the lower sum and the upper sum here. So even though my lower sum and upper sum are getting closer together, they're going to kind of sandwich that value, which is 5.42. I know most of you guys being, let me go ahead and delete these out so it's easier to see. I know most of you calculus folks, would probably prefer to have a rectangle sum. So there is a rectangle sum. Notice there's an additional parameter at the end. It's a position for the rectangle start. So I will go f, x of A, x of B, n rectangles. And if I want my rectangle to be at the midpoint, I'm going to use 0.5 for that final parameter. And so these rectangles are all at the midpoints. If I change that parameter from 0.5 to 1, then the rectangles are determined by the right endpoint. And if I change the 1 to a 0, the rectangles will be determined by the left endpoint. So that is the rectangle sum. And then, of course, there is an integral, and that would be integral. And I will go f, x of a, and x of b. And that gives me my true value. So you could compare all of these different Riemann sums, if you'd like, to the true integral. And you could notice how some approach that value from above, some approach it from below. Some are better estimates than others. But this gives you a chance to really explore that dynamically. And more importantly, your students can do this themselves.